And I'm recording, don't worry.
All right. All right, guys. Well, it looks like we are just about ready to get started. We'll let Dr. White get ready.
Yeah, whenever we're ready to start, it's what, a minute or two, we'll start.
Yep.
See what all we've got here.
Good morning, everyone.
Good morning, James.
Good morning. How's
Good
everyone?
morning.
Everybody ready?
We are. I am. I'm excited. It's like game day. Woo!
Are you ready, Jim? We're playing musical host. If you want to be host, you can be host.
We'll see how many people we can make host.
I would know what to do if I was host.
Oh, I think you would.
Colin, you're looking very nice.
I know, everyone looks
Thank you.
good.
Got the tie. Underdressed. Dr. Wade has the tie.
Michael, quick question. Are you say May 12th to 14th?
Are you back? Are you in town to meet on those days?
Yeah, hold
I
on.
text.
Anytime after May 12.
Anytime after May 12th.
Yeah.
The 13th I can, the 14th I start teaching. So the 13th
Okay.
would be optimal.
But
13th.
on
Okay.
days that you're not, are you teaching Monday and Friday or what is it?
It's just Friday mornings, all Friday
Okay.
mornings.
All right. So, okay. All right. All right. We'll set something up.
Okay, 13th sounds good.
Okay.
We ready to start, Dana?
I think so.
All right.
Go ahead. Take
All
it
right,
away, Dr.
well-
White.
Good morning, everyone. I'm Professor Bob White, and it's indeed my pleasure to welcome you to the 68th Senior Engineering Design Conference hosted by the College of Engineering and Applied Sciences and the Department of Industrial and Entrepreneurial Engineering and Engineering Management. We're very happy you're able to join with us this morning and that the technology allows all of us to join in this virtual conference. And this is our third time for the virtual conference. So it has some real advantages that allows lots of us to join that may not be able to otherwise. There are several groups we'd like to extend a warm welcome to, and that includes fellow students, faculty, visitors, friends, project sponsors. Thanks to all of you for being here this morning and for supporting the students. Another group we want to particularly recognize and spend a warm welcome to are parents and family members that are able to be with us. While it's not always possible to join, we like to recognize those that can. And this morning, we'd like to recognize Chuck and Sue Whitman, parents of Colin. Chuck and Sue, want to raise your hands and say hello to the group? Thank you very much for joining with us, and thank you for sending Colin to be part of our program. We've enjoyed having him here as a nice young man. Thank you very much. These students, almost engineers, are very thankful for the love and support that all of us, all of you, have given them and made it possible for them to be here supporting their projects. This is a very exciting and proud day for our seniors. They've worked very hard for several years to reach this point. And for us as faculty, it's very rewarding to see these young people grow into confident and competent and capable young engineers. We're sure you'll be very impressed with their presentations. The first presentation this morning is developing a process to reduce warranty claims at an RV manufacturer. The student presenters are Abigail Lee, Jonathan Shea, and Colin Whitman.
Hi, welcome to our senior design presentation. My name is Colin Whitman. My partners are Abigail Lee and Jonathan Shea. For this project, we are developing a process to reduce warranty claims at an RV manufacturer. In today's presentation, we will give you a brief background of our project, including introducing our advisors and sponsor. We will also state the objectives of the project while providing an overview of what was completed over the course of the last 2 semesters. Additionally, we will look at our data analysis and discuss our recommendations being given to the company. Finally, we will address the results of this project, including a brief cost analysis of the system, and answer any questions that you may have. Our faculty advisors are Dana Hammond and Dr. Jim Burns. We worked with Forest River RV. Forest River RV is a division of Forest River Incorporated, which was founded in 1996. They are one of the largest recreational vehicle manufacturers in North America. For this project, we worked specifically with Plant 70, which was located in Topeka, Indiana. Plant 70 produces several of Forest River's high-end fifth-wheel models valued at over $130,000 per unit. The plant produces roughly 4 units per day. Most parts of the RV are manufactured in-house, allowing for more customizable designs and floor plans, depending on what customers want and what the company is willing to provide. Each unit requires about 8 days of work from start to finish. The top picture shows the beginning stages as the empty chassis has axles and tanks installed before the floor is then put into place. This chassis is then placed onto rollers and a track, as is seen in the middle picture. As each step is completed, it is then possible for a couple of workers to simply push the entire unit onto the next stage of the assembly line. The bottom picture here shows a unit at the end of the line. The only possible steps remaining are for decals to be placed or a full body paint job to be completed. The RV industry is seeing an overall increase in sales annually. Despite the pandemic, the trend has gone from one of decline to one of rapid increase. Even with several months of lost sales due to closures and shutdowns, sales went from 406,000 units in 2019 to 430,000 units in 2020, with current projections saying they will surpass 502,000 units sold in 2021. The graph shows the past 10 years of annual RV sales by unit in the United States in orange, while the gray line shows the trend of total warranty claims cost at Plant 70 over the last 5 years since its opening. Sales are clearly trending upwards with projections of record-setting years on the horizon, and warranty claims show a pattern of following annual sales trends with about a year's delay. This means that Plant 70 should be anticipating a rise in warranty claims cost over the next several years at the very least. Our objectives in this project are to reduce warranty claims, which are currently costing the company an average of about $41,200 a month. Additionally, we wanted to design a system that would reduce the gap between claims data and production, along with allowing for the identification of process improvement opportunities. To reduce these claims, we first analyzed what the potential causes were. As can be seen in this fishbone diagram, these causes were broken down into 5 categories, which included people, processes, documentation, suppliers, and measurements. In terms of people, Plant 70 has a high level of turnover and does not have any standard training procedures for new employees when they start. Processes also lack any form of standardization, with very little documentation being done that could be of use in a feedback loop to ensure quality production. Suppliers are not always thoroughly vetted and must only meet some minimal criteria. Finally, in terms of measurements, validation and audit systems are limited or non-existent in most cases. After observations and studying these areas, a couple of common themes were determined to be a lack of standardization and documentation within the manufacturing process and the plant as a whole. These shortfalls have allowed for a lack of quality in the completed product and can both be addressed by the same initial steps of creating a more thorough quality check and documentation system to catch errors before the product is shipped and help prevent them in the future. To approach this problem, we first had to determine what issues should be addressed to best reduce warranty claims frequency and cost. The first thing done was an analysis of operation descriptions and their frequencies to determine what would have the greatest impact on the problem being addressed. After graphing the frequency of each operation description, it became obvious that no single operation description would have a dramatic impact on the number of warranty claims being filed. The top 2 descriptions accounted for roughly 2% of claims each, while everything else was substantially less than 2%, with more than 1,000 individual operation descriptions being listed. With time constraints, possible cooperation issues, and current developments in the facility, our team has decided on the implementation of a new inspection process. This inspection approach will act as a preventative measure to reduce warranty claims by catching mistakes that will lead to claims before each unit leaves the facility. Additionally, documenting these inspections will create a feedback loop with production for future unit construction as well as validate manufacturing processes and methods. Finally, this system will lay a foundation for future efforts in standardizing work and continuous improvement. The current inspection system within Plant 70 consists only of visual checks with little to no documentation being completed. This system does not allow for easy tracking of errors and introduces a high risk or potential of errors being missed and allowed to ship from the facility. Additional inspections are carried out in another location. These inspections are known as pre-delivery inspection, or PDIs. However, this facility was not open until July of 2020 and only has the capacity to inspect 2 units from Plant 70 per week, meaning that the majority of Plant 70's production still will not get a thorough inspection before shipping to dealerships or customers.
In order to pinpoint areas to improve inspection, we looked at the warranty claims data. The data analyzed stretched from 2016 to 2020, coming to a total of about 11,000 claims. The flowchart here shows how the warranty data is organized, the most general category being failure descriptions such as installed improper or loose. These describe the source of failure that caused the claim, and there are 73 in total, but we only show 3 here for simplicity. These are then further divided into operation codes such as adjust. These explain what type of action was done to resolve the claim. Again, only 3 are shown, but there are 23 in total. And it is important to note here that these can appear under any failure description as they are not dependent upon one another. And then lastly, we have the operation descriptions at the bottom. These explain exactly what component failed. Here we see the cost and frequency distribution of the top 6 failure descriptions. Since there is a lot of subjectivity involved when uploading warranty claims into the system, we decided to focus only on manufacturing related failure descriptions. These are shown in the red box here. We see that these account for 40% of all frequencies and 31% of all warranty costs. We then looked further into these 3 manufacturing-related failure descriptions by seeing what their top operation descriptions were in terms of cost and frequency. It's important to note that these operation descriptions are very specific. For example, R&R drawer guides and tracks only accounts for drawer guides and track claims that are under R&R and not misaligned or loose. Because of this, only 1 to 4% of costs and volumes are shown here. This again reinforces the conclusion that there is no single area that significantly affects the cost and frequency warranty claims. So our team decided to create focus areas shown here based on the operation descriptions to encompass more areas and issues that need inspection. Here we see the cost and frequency distribution for the 8 focus areas. Based on the numbers, we decided to focus in only on the top 4, being cabinet, trim and molding, entry door, drawer guides, and tracks, to move forward with our project since each area consists of many claims to sort through. In total, these 4 account for about 21% of the total claims and 11% of the total warranty cost. Moving forward, we utilize these 4 focus areas to create our inspection system, such as checklists and other elements. To begin creating our checklist, our team performed a cross-analysis between the focus area warranty claims and the PDI data. Again, PDI is the pre-delivery inspection that happens off facility. We found that with the frequency of PDI inspections and the time between invoice and claims being made, that out of the 26 units that have been PDI inspected, only 17 of them could possibly show up in warranty by now. We cross-analyzed these 17 units to see if they did indeed come back to warranty with issues in our focus areas, and about 53% of them did. We also then cross-analyzed the focus areas with the PDI inspection checklist. This was done to identify gaps of what should be inspected and if they are being so. Here are the resulting inspection criteria from the cross-analysis. These are issues in our focus areas that we found were not being inspected at PDI and were implemented into the design of our inspection system.
Moving forward with the project, we used the PDCA model to frame our recommendations. PDCA stands for Plan, Do, Check, and Act. We chose this model since it is used to carry out change, and repeating the cycle of this model will implement continuous improvement. And for our project, Plan is represented by the actual planning of the inspection system, while Do is represented by the inspection itself, where we created checklists and procedures. The check is represented by the quality goal that is monitored by a Gimbal Board, which is a way to visualize continuous improvements. And then this leads to the Act portion of the model, where we use the board in Gimbal meetings to identify and execute continuous improvement. Next, we put together a proposed inspection checklist based off the identified inspection criteria. This checklist is intended to be used on a tablet, which will make it easier to include photos of findings. It'll also be easier for record keepings and make the results pretty much available immediately. The checklist is broken down into rooms of the unit and the focus areas that apply to that room. On the right here, you can see an image of one of the unit layouts. And this layout is broken down into 4 rooms: the bedroom with the green box, the bathroom with the yellow box, and the living space has the blue box, and the kitchen with the purple box. Here we have an example of our proposed checklist to be used in the inspection. Highlighted by the green box at the top of the checklist indicates where the unit information is going to go. And then the next box will be where what is being inspected, which is shown here as cabinetry. And then the next area shows the room that is being inspected, which is shown here as kitchen. And directly below that is the inspection items, which are based on the inspection criteria that were identified. And to the right of that is the accept and reject of the inspected items, which you can see below, that is indicated using the inspector's initials. And by using the initials, they can be used as a reference for a point of contact for any further questions or maybe later analysis. Last is the remarks area. This is where remarks for a rejected item will go, as well as any indication of any photos that were taken of that item. Now that the checklist has been created, we created a standard procedure for the inspections. The procedure has an instruction on how to use the checklist and carry out the inspection of each item. For an example, the instruction states that the checklist to be used in each area, checking that entire area for each item before moving on to the next area. Then in each inspection item is described to ensure that the inspections are done exactly the same no matter who carries out the inspection. Similar items are described once and then referred to that section in the instruction for other areas that use the same instruction. And an example of that would be the procedure for inspecting trim would apply to areas such as ceilings, floor, window, and door trims, rather than describing each one individually and it being repetitive.
So another element of our recommended inspection system is a Gimbal Board, which will be used as a medium through which the inspection team can continuously monitor their projects and system performance visually. So the Gimbal Boards show the links between the analysis that the team completed and the improvements implemented. They also allow members of the team to see how their ideas and efforts are contributing to the overall goal and project of inspection. The Gimbal Board will be on a 48x60 whiteboard on wheels for mobility and flexibility throughout the inspection area. These will be utilized during a 20-minute morning meeting attended by the inspection lead, employees within inspection, and management that occur on a daily basis before each shift. This here is our proposed Gimbal Board. It is divided into 4 color-coded sections: black, blue, red, and yellow, with a suggestions box at the end. In the top black box is the overall improvement goal of the inspection station. This will be reviewed every morning at the start of the meeting to reiterate the main goal of inspection. The next is the blue section. These are the key performance indicators relating to inspections, such as number of inspections, inspection duration, frequency of quality, and etc. After stating the improvement goal, the team leader will review the KPIs and how they have changed and what these changes mean to the team. The red section here focuses on specific improvement projects that are in progress. Each employee in charge of a quality improvement will go over their project, the status, and the next actions that will be taken. And then we have the yellow section at the bottom. These focus on the most current findings from the day before, such as safety metrics and any red flags that were found during inspection. The team lead will go through each of the red flags identified from the day before, and then together they will brainstorm what the next actions will be to counter them. And then lastly, we have the suggestions box, which will be the last part of the morning meeting. Any reasonable employee suggestions that are approved through management will be explained at this point in the meeting, and recognition will be given to the employee who suggested.
Next, we did a cost analysis of the inspection process, which started with an interview with a quality inspector from a different Forest River plant to help identify what current labor rates are and items that we thought would be needed to start a similar inspection process. The items were then researched for costs and the life of the items. Next, we had to determine the amount of labor that will be required for the inspection. And to do this, we conducted dry runs on a unit, and it was determined a standard time of 41 minutes per each unit. This table indicates a breakdown of the labor and items put into monthly costs. The next step in the cost analysis was to determine the direct cost of claims that could be saved through the inspection. It is important to note that the cost used for this was only external costs paid from Forest River to the service centers doing the warranty work. This means that the internal costs of warranty personnel that may be filing the claims, the shipping department, and shipping parts, etc., is not included. And for this explanation of the cost calculation, 75% was used as an example in this table for the average savings. Next, we found through research what percent of the warranty cost could be included as a goodwill due to customer satisfaction. This is based on the lower frequency from the inspections and was determined to be 33%. The cost analysis was then applied to the 4 focus areas that our team designed the inspection system for. We also wanted to include the 3 manufacturing failure codes to show the potential of the inspection system when it's expanded. And with this example, using the 75% for the average claim savings and the increase of goodwill minus the monthly cost of inspection, Plant 70 would save near $4,000 a month just on the 4 focus areas. And it also has the potential to save close to $13,000 a month, expanding the inspection to the top 3 manufacturing failure descriptions. And since the average claim saving is not known until the inspection is implemented, we made a cost savings sensitivity graph to show the percent of claims saved through the inspections. If you look at the blue line, it represents the top 4 focus areas and its cost savings. Where it meets the orange line, you can see the inspection is right around 23%, which indicates the percentage of claims needed to be saved for the cost to break even. The cost savings go all the way up to $6,000 a month from there. And then if you look at the gray line, it represents the potential of the system by including those top 3 manufacturing failure descriptions. And where it meets the orange line is the break-even point, right at 16%. And the cost savings going up to $18,000 a month. Through the implementation of this inspection system, the company goals of reducing volume and cost of warranty claims can be accomplished. This system will be a proactive approach to product quality, allowing for implementation of continuous improvement through the creation of a shorter feedback loop, from the final product quality to the production floor. We'd like to open the floor for any questions.
If anyone has any questions, please unmute and share your questions with us. The team has a few minutes to answer them.
I have a question. Should be simple, quick. Based on the attribute study that you did, so the pass-fail results, kind of on that checklist that you showed, would you recommend that they perform like 100% inspection or kind of follow like a sampling plan?
Right now, since that they only are doing 4 units per day, we recommend that they do 100% sampling.
Any other questions?
Anyone else? Anybody have any questions for this group? Very good. Well, thank you very much, everybody.
Thank you, guys. Well done.